Swing to the beat where the pixels play. From rendering to VR, it's a pixel array.
Yeah, thank you, Martin, for the nice introduction. And thank you, of course, everybody for taking the time being here today. So I'm very honored to be able to give the keynote here at CESC this year. I myself remember quite well my first CESC and also the keynote talk that was given there by Joachim Horcher. And it was back then actually very motivating, very inspiring. And in that spirit, I'd also like this talk to be three things today. So I would like it to be, first of all, an introduction into the topic of 3D Gaussian splatting and its use cases for anybody who hasn't heard about it yet, or maybe has heard about it at the fringes, but has no clear idea what actually all the fuss is all about. But I would also like it to be a lesson, a small lesson for opportunities and challenges of international collaboration, and then maybe you can take something away from this talk more than just learning about some computer graphics methodology. Because I very well remember when Joachim Horcher gave his keynote talk and then very surprisingly just hit the table to basically give a nice impulse, basically get everybody's attention, so get the focus back on topic, right? So he basically back then gave a lesson on how to keep the viewers and the audience's attention. So I also want to provide some sort of lesson that you can carry on forward into the future. And finally, it should also be a little bit of an inspiration for the outlook and predictions of what is to come in the field of computer graphics and particularly Radiance fields. So let's talk a little bit about 3D Gaussian splatting. So first of all, what is 3D Gaussian splatting? It's a method for novel view synthesis. So that means basically you have some views that are given to you in the form of images, most likely, and the camera positions from which those images were taken. And now you want to produce new views that are not part of the set that is input. So you're basically extrapolating novel views from known views without having seen them before. And this is called novel view synthesis. Now, our goal with 3D Gaussian splatting, this topic or this methodology or this whole problem is not new. It's been around for ages, for decades. But with 3D Gaussian splatting, what we really wanted to solve is we wanted to have this novel view synthesis at rates where it actually enables real-time rendering. So those unseen views are produced while you are going through the scene live. We wanted to have high quality, something that would rival maybe the best approaches currently out there. We wanted it to be somewhat fast and easy to obtain, and also to be reasonably compact. So that would basically be our dream realization. That would be a method that is portable, that is easily applicable, and that is also highly performant. So as a first testament to international collaboration, I want to outline the team that was involved in the 3D Gaussian splatting project. So first of all, there was me and Yorgos Kopanas. Both of us joint first authors on this project. And Yorgos, with his background on point-based rendering, basically had a lot of previous work already invested into this, and had also spent quite some years to convince George Drettakis, the head of the GraphDeco group at INRIA in the University Côte d'Azur, that there is actually something to point-based rendering. Now, this fit very well with my expertise because the years prior to this project, I had spent at TU Wien with Michi Wimmer and Markus Schütz, also looking into all kinds of point-based rendering and how to do it quickly. And then also, of course, there was the vital help of Thomas Leinkühler from MPI, who has given us very great mathematical insights, has a very clear and analytic mind, and loves to look at problems and twist them around, look at them mathematically, and then come up with the most sensible solution and the most creative solutions in some cases. Now, I would like to point out configurations, and I would like to initialize here, or basically initiate here, a scale for evaluating the work conditions in these different collaborations that I'm going to talk about. So if we're talking about INRIA, which is spread all over France, which is the Institut National de Recherche into anything that is informatics and computer science, basically there's many locations throughout France. But I would say this one in the University Côte d'Azur is somewhat special because the head of the GraphDeco group in which we work there is George Drettakis. And George Drettakis ensures that there's both a very significant amount of urgency in the work that is being done, and also there's a significant amount of thoroughness. So that means there is some continuous pressure being applied to you to actually get your work to do something. That is the urgency. And then there's the thoroughness. That means the results are double and triple checked, and this is possible because George Drettakis is very much hands-on, and he looks at the work, and if you show him an image, he can tell whether it's fake, whether it's computer generated or real, and he can also tell if something was basically cocked up in producing that image. He has a real knack from decades of looking at all kinds of images to basically make that distinction. So this would be the first configuration that I would like to highlight here, basically working both with urgency and with thoroughness. And I would say the result of this configuration was the 3D Gaussian splatting approach, which basically, if you start from something that is a somewhat coarse point cloud, you can then go and optimize from these points Gaussian splats, and these Gaussian splats are then, with gradient descent, optimized to actually fit the images that you provide. So the known set of images is used to optimize the entire 3D scene representation, which you can then turn into a 3D renderable configuration of Gaussian splats, and from novel views, they can then produce novel view images. So the training process of these Gaussians looks something like this, in case you've never seen it. So starting from initial Gaussian points in space, you keep optimizing them, and with gradient descent and some additional mechanics that I'm going to talk about later, basically over time they start to fit the images that are depicting an object of interest in 3D quite accurately. And then after training from this 3D representation, you are free to choose new novel views. Now, there has been some great advancements in recent studies. One of the most impressive, if we want to keep up with the highest quality version of 3D Gaussian splatting today, is probably the 3D Gaussian splatting as Markov chain Monte Carlo. And this was done by Kwang Yi and Andrea Tagliasacci, so there was some significant collaborations here between the University of British Columbia, Google Research, Google DeepMind, Simon Fraser University, and the University of Toronto. And these results that we are seeing here are the usual suspects that you look at when you scour the latest 3D Gaussian splatting paper. You basically look at the individual scenes or test suits that you are interested in. So we see these here, for instance, Mipner 360, tanks and temples, and deep landing. All of these are sets of images on which the novel view synthesis generation is evaluated. And then we look at these error metrics, which are basically the usual suspects again, PSNR, SSIM, and LPIPS, which are so far our best tools for evaluating whether one image matches another one perceivably or perceptibly. So the higher those numbers for PSNR and SSIM, and the lower those numbers for LPIPS, the better, usually. It becomes, in many cases, a hunt for getting the best numbers with the most emphasis or the most impressive approach. And 3D Gaussian splatting, after starting from those SFM points at initialization, basically can use Markov chain Monte Carlo to not start from those informed points that you usually get from structure from motion, looking at the input images, but actually from random points. So now you have the opportunity to put random points as a starting position, not those informed ones that you actually get as feature points from those images, but then just use some random noise and from there move towards a really high quality reconstruction. So where are the Gaussian splats that can be initialized from random points and then optimized to get very high quality reconstructions, very true to the actual ground truth images? Where are those Gaussian splats useful? Well, what we've seen recently is not only the reconstruction of these still scenes where nothing moves, but they can also be very trivially extended to dynamic scenes. So we can also have 4D Gaussian splatting. We're basically just extending those 3D Gaussians with an additional attribute that gives the position or their functions or their scale or their opacity as a function of time. And now you have the ability to actually do dynamic scenes, sequences and videos instead of still scenes. You can also apply them to inverse rendering. So you can have a reconstruction of the scene as a still image, and then basically try not to defer only the color of those Gaussians, but if you have some assumptions about the material that is present in your scene, or maybe you have a general BRDF that you can say is capable of modeling a reasonable amount of materials, you simply give that to the Gaussians as a surface parameter, and then you optimize those physically based BRDF parameters, and you have a scene that is now relightable. Also, we have seen 3D Gaussian splatting as a very valuable tool for generative AI for 3D content. And there's many other applications of 3DGS that is being used for. So for instance, we can have surface reconstruction. We can, from these reconstructed 3D scenes, actually try to fit some surfaces through those eventual Gaussians and where they end up in space. And we can have fast structure from motion and multi-view stereo. And also, we have some initial approaches towards using those reconstructed 3D scenes as the basis for doing simulations. So for instance, physics on the Gaussians, interpreting them as density in space. And a very particular application is the use for human avatars. Now the Gaussians, because they are able to basically move freely in space, become very long, become very thin, become very detailed, they are extremely good at modeling those fine details that people tend to recognize when they are missing in a 3D model of a human face. So 3D Gaussian splats are extremely usable for human avatars, so much so that actually there was a full session at SIGGRAPH Asia of just using 3D Gaussian splats for modeling human avatars. So this is a very, very active field. Now that we know that 3D Gaussian splatting is effective at certain very desirable topics or tasks, how can we actually put it on other devices, or how can we actually bring it to the masses? So the initial implementation of 3D Gaussian splatting was done with an elaborate framework that basically relies on some CUDA kernels, relies on some Python code, basically pulls from all the sources together, and if you're lucky, you can compile all the libraries and you put it into one executable and then you run it, maybe not, right? It's a research project after all. But the fun thing about 3D Gaussian splatting is that the rendering of the reconstructed models is extremely straightforward. So straightforward, actually, that all you need to visualize a trained 3D Gaussian splat model is your standard graphics pipeline. So if we look at the blending formula, and this is the formula used for volume blending, it actually goes back to the NERV paper by Mildenhall and colleagues. If we use this volume blending formula that is being used for blending those Gaussians back to front to back, we actually see that this can be very easily implemented in your standard OpenGL pipeline. So for instance, you could define a pipeline that looks like this, where as a vertex shader, you start off with the position of the individual Gaussians that you have in your scene, and that initializes where they should be placed. You then figure out, in, for instance, a geometry shader, using the standard deviation of the Gaussian to create a quad that encloses correctly all the pixels that should contribute, that should be filled and affected by that Gaussian. Then you run a fragment shader, and that fragment shader basically decides for every pixel inside that quad what is the corresponding function in the Gaussian, and that will define its opacity. And then with this opacity, basically all you have to do is to render those Gaussians with a very standard blending function. And this simple blending function actually maps to just two very simple commands in OpenGL. All you have to do is make sure that your background for rendering is cleared to an empty field, and you have to use the GL blend function that is described here. So basically with this setup, all you have is these two settings that you need to ensure, and after that, rendering your 3D Gaussians in a standard OpenGL pipeline. So basically on any device that supports OpenGL is a piece of cake. So basically that means that 3D Gaussian splatting rendering is super portable. So we are actually going towards this, having 3D Gaussian splatting everywhere quite easily. Now, what about reducing the size of the 3D Gaussian splatting scenes? Because that's the one part of the 3D Gaussian splatting scenes that is actually quite unattractive about them initially, right? So 3D Gaussian splatting viewing is not yet fast and portable because we have decent training speeds, we have decent rendering speeds, but if you look at the data sets and you say, for instance, I have stored my data, I have it on my local hard drive or I have it somewhere on a server, downloading it or fetching that data is not that fast. Why? Because the files that the initial approach for 3D Gaussian splatting generates was very, very large. And this is for a good reason, and I'll come to that in a minute, but you're basically looking at dozens of megabytes to easily more than 1 gigabyte. So for a single scene, maybe for a single object, that's not very portable. You don't want to download several dozens of megabytes or even more than a gigabyte to look at a simple pair of shoes that you are trying to view on your phone. So it was at the time smaller than the more data-hungry Planoxels approach, but it was much, much bigger than the very competitive NERV scenes at the time. So what can we do about the 3D Gaussian splats? Well, we went to go, and this is again some work that we did with INRIA, shrink down the 3D Gaussian splatting scenes and see what we can do about their size. So first of all, we need to look at 3D Gaussian splatting scenes and why they are actually so big. So each of these Gaussians that we have in our scene is actually quite dense with information. We first of all have 59 individual attributes, all of them in floating position stored per Gaussian, and then we have millions of Gaussians. So basically we are throwing things at the wall and seeing what sticks, right? We don't probably need those millions of Gaussians, but the initial approach basically was trying to get the best quality and take no victims, right? So basically be as aggressive as possible. And in doing so, it produced these very, very large scenes where there are millions of Gaussians and huge, huge file sizes, and each of these Gaussians then also is very, very expensive. Now this brings us to continual work that we did with INRIA, where we were looking at, first of all, how we can strategically identify the memory cost and then bring it down by prioritizing the estimated contribution of each of the quality that each byte in these attributes basically contributes to the total image quality. And we came up with a three-pronged approach where we used a method for pruning superfluous Gaussians. We did some selective spherical harmonics or color initialization and activation, and we used some standard compression methodologies that are fairly common in the literature, which is code booking and quantization. So with all these in place, we then evaluated everything for a quality and storage trade-off, especially with a focus on mobile rendering. So how can we visualize this, or how can we imagine this? If we start from the Gaussians representing a scene, basically the first stage is to take those Gaussians that are not contributing a lot. Basically they are superfluous. So you can imagine points in space that are almost completely see-through, or points in space that basically do the same thing and are completely overlapping and looking entirely exactly the same from all directions. And this would be just two examples of configurations where there are Gaussians in space that are not needed or are basically redundant. So what we do in the first case, in the first step, is to identify those redundant Gaussians and regularly prune them during the optimization of the process. So whenever we hit a certain number of iterations, basically find the Gaussians that are most likely not needed, removing them, and optimization, this is an important part to notice, is really quite robust. So even if we remove some things that were actually very vital, optimization with stochastic gradient descent will find a way and will very much try to compensate for the mistakes that you made. So it's actually quite forgiving. Now, the second part is that, of course, you can apply some common sense and you will realize that there are some parts of your scene that are complex in terms of light interplay. So some parts of your scene might be very reflective, might be refractive, and those will need all of the configurations for color, which we encode with spherical harmonics in the Gaussians. So basically the complexity of this light interplay and of these view-dependent effects is determined by the number of bands of spherical harmonics being used. So if we have some parts of the scene that have these complex view-dependent effects, we can identify them, and we can give them all of the spherical harmonic spans that we have available, something in the range of 3, 4, or maybe 5. And then there's also clearly other parts of the scene where everything is very simple, monochrome, and diffuse. And these regions you can get away with much less, maybe even just one band of spherical harmonics. And this has a significant impact on size and allows you to make the scenes, again, much, much smaller, this time not by reducing the number of primitives that you're using, but by adapting actually dynamically the size of each individual primitives and how detailed they are and how many attributes they store. And the last part that we can do is to look at the values and how they are distributed for each of these attributes that remain. And so the remaining attributes will usually very commonly cluster in certain ranges. And this is a very great use case for using something like code booking or paletting. So if you've ever worked with a paletted image, you basically know this concept, right? For instance, an image that is mostly blue or violet or purple, you might be able to come up with a color palette that has exactly those ranges and those hues of color that you're interested in, and then you can use that palette basically for the available colors that you want to be able to show in that image, and then just index each pixel into your palette. So this is a very, very old way, for instance, of doing compression of image data in video games. And it also rings true still today. Basically the same approach works here quite well. And with all these techniques combined, the initial size of the 3D Gaussian splats can be brought down by a factor of 30 times or more. So we're now moving from the initial approach that was fast and high quality, but bulky, to a portable approach that basically can be rendered everywhere, and also the file sizes are now coming down. Okay? So we're making some significant progress here with the method. So it's actually going towards this very nice and very portable, let's say, ubiquitous method. Now we are more efficient and more compact. And usually, when you have something that is compressed, like a zip file, if you want to get to the data, it actually takes now more time to do that, right? Because you compressed it down. But not in this case. So with these methods that we just showed, these compression methods, actually getting to the data and interpreting the data and turning it into images becomes faster. Because the pruning actually means there are simply fewer Gaussians, right? There's fewer primitives to put on the screen, so less work. And also the selective spherical harmonics means there's simply overall less data to fetch. And if you know your graphics processing unit, the graphics processing unit is always happy if it has less data to fetch. If you can replace some data fetching with some slightly more involved program logic or some arithmetic, you should definitely do that because the GPU will be very thankful. And finally, the code booking actually seems like an indirection, like a lookup into memory that you didn't have before, but actually it results in a higher probability of achieving cache hits again on the graphics processing unit. So basically, overall, it achieves better rendering performance if you use these compressed models. And it's not us so much that found the most impactful example of this, but actually other colleagues, Niedermeyer and colleagues who did this research and basically presented it, I think, somewhat simultaneously to our research, but with a stronger focus on actually faster rendering, which was quite nice to see. Now, as an example here, because our argument was we wanted to be portable, we wanted to run basically everywhere. So running on your phone the standard visualization with the baseline file sizes, 280 megabytes for one scene, basically takes quite a significant amount of time. And on the left-hand side, we actually see the lifetime or the online time it takes to download the entire file from a remote server and then run it on the phone, even with a slightly better frame rate in real time. Okay? So the next part is, I previously showed you that thoroughness and urgency graph, right? So those bars were not maxed out. Okay, so what does that mean? We were quite thorough when we did the 3D Gaussian splatting approach and when we developed it, but we were not as thorough as we could have been. Okay, so there was some room for additional thoroughness, that we did not go into when we made the initial method, because actually it was developed in the space of 5 or 6 months or so, right? So we actually were, let's say, a little bit in a hurry, and it initially wasn't even supposed to go to SIGGRAPH. We thought, this might be a nice SIGGRAPH Asia paper, until somewhere around Christmas we basically discovered, wait a minute, we have something here, right? Let's try and see if that can make it into SIGGRAPH. So that's how we submitted the 3D Gaussian splatting paper initially. But we were not as thorough as we could have been, and this is what this next paper here basically tries to solve. So if you look at how primitives that are volumetric in nature are rendered, you would have the simple and very intuitive idea that if I have an elongated ball of particles, this ball of particles, elongated, so basically anisotropic, should look denser or should be occluding more light if I look through its long side than if I look through its thin side. That's a very intuitive idea, because the number of particles or the density of particles that you are seeing along one axis is more, so there's more particles seen along one axis, so they should be blocking more light than along another axis, than looking through the thin side of the same elongated ball or Gaussian, right? So, and if we look at what 3D Gaussian splatting was motivated by, which is some early work called elliptic weighted average splatting, actually this original work sticks very true to this first and intuitive impression, but 3D Gaussian splatting does not, right? Somewhere along the way, we made a mistake, or we left out some variables, or the math got a little bit too confusing. And now, whether you look at a Gaussian through its thin side or through its thick side, it basically always, at its center, occludes the same amount of light, which physically doesn't make much sense. And this is exactly what we addressed in this follow-up paper, which is, does 3D Gaussian splatting actually need accurate volumetric rendering, which was some nice work with TU Wien and also in collaboration with INRIA, where we resolved this in very much detail. So to bring back my urgency and thoroughness scale, here in this scenario, this was work that we knew it wasn't very contested, or it wasn't very contended. That was a problem that we were looking into, and it was highly theoretical, but also there was not that much reason to look into it, or there was not that much pressure to actually resolve it, because 3D Gaussian splatting was working sufficiently well. Actually, it was working quite well, so there was quite little urgency to push into this research and put it out as fast as possible. So we took our time, but we were very thorough in this research, okay? So this is an example of a paper where there was not much pressure, not much urgency, and we had all the time in the world to actually figure out the math, go through it 3, 4, 5 times until it made sense, and then also formulate it in a way that is still readable to the viewer. And this was a collaboration of TU Wien and together with the guys at INRIA, because both George Drettakis and Yorgos Kopanas really wanted to have, once and for all, resolved all the mistakes that we might have possibly made in the initial initial publication. Now, coming back to the point of low urgency, as I said, 3D Gaussian splatting was really working quite well already. So does it actually matter? And the bottom line was, yeah, kinda, but this physically incorrect approach that we initially came up with, basically out of coincidence, was already working so well that you have to really, really push the parameters to actually make it come out, that there are some errors in the original approach, right? So if you, for instance, have a scene and you have a very, very low number of Gaussians available, you can see some benefits when you use the volumetrically correct formulations, but actually as you keep throwing more and more Gaussians at the problem, the differences become very minor until they are no longer actually really seen, okay? So this was some interesting aspects, but since there was no significant problem that needed to be solved by correcting this, the urgency was lower and we had the time to work on it very thoroughly. Now, there's another approach left that we need to look into, because 3D Gaussian splats, being portable, being compact, being easy to render, still have the problem of popping artifacts. So now we have our smaller models, we have our portable models, and is that the end of the story? Unfortunately, this is not the case because we have problems in interactive rendering. So by reducing the Gaussians, you basically need to make the Gaussians that remain themselves larger, right? So if you have 1,000,000 Gaussians to model a simple scene, and you say, I want to reduce this down to maybe 100,000. Now each of these Gaussians that remain have to take on more of a job, so they probably will become more expensive in space. And this will lead to an increased occurrence of popping artifacts due to the somewhat approximate sorting in 3D Gaussian splatting. Now, what does that mean? I will come to this in a minute, but the solution to this was an approach that we developed with TU Graz and TU Wien called Stop the Pop, where we took sorted Gaussian splatting for view-consistent real-time rendering to reality. Now, regarding the thoroughness and urgency configuration for this project, this was purely a project between TU Wien and TU Graz, so both of those were Austrian institutions. When you work with TU Graz, the team that was led there by Markus Steinberger, I would say there's always a certain sense of urgency, right? So Markus Steinberger is a very capable professor at TU Graz, soon to be a full professor and leader, I think, of the CG group there, and he will instill some sort of urgency. So both because the topic was somewhat more relevant, we knew that other people were also looking into this, but also because of the people involved. In this case, it was very much the lead of Markus Steinberger, who simply by being present added some urgency. We had more of a drive to actually bring this forward. Now, the popping artifacts can be seen here quite clearly and quite evidently. So whenever we basically start moving the camera, we see that the Gaussians are not very coherently sorted. So they basically pop all over the place. Let me visualize that maybe in a little bit clearer aspect in the next scene. So the rendering of the 3D Gaussian splats, much like your standard GPU pipeline, is doing it in tiles. Yeah? So every Gaussian, when it is being rendered, first of all, looks at the screen and subdivides the screen into individual 2D tiles, and then the Gaussians are sent to the tiles that they overlap with. And they basically go into a little queue for each individual tile, and then each tile processes that queue and blends the Gaussians according to the formula that you already see. So the Gaussians are not sorted per pixel, actually. So visibility of these Gaussian primitives is not resolved per pixel, but only approximately once for the 3D positions view space Z coordinate. So there's one depth value for every Gaussian in every pixel. And this might sound okay initially, but if we visualize, this actually indicates quite a significant problem, because this means if there's only ever one depth value for an entire Gaussian, that means a Gaussian is either completely in front or completely in the back of another Gaussian. And this is exactly what leads to the popping artifacts that we see in the original approach. Now, again, remember that initially those Gaussian files and those Gaussian reconstructions were huge, millions of Gaussians, right? Because we didn't care about memory. So these popping artifacts actually weren't that big of a deal. But now you go ahead and say, well, I want to bring down the number of Gaussians to what I really only need to model the scene. So now you're reducing the number of Gaussians, they all become larger, and now popping actually is a very significant problem. Now, what did the team of Markus Steinberger and his very capable PhD students do? They approached this from a GPU engineering side, as they usually do. So basically, they came up with a very smart idea of using a multi-queue stack, so having incrementally finer and finer queues, which are getting smaller. So having basically, instead of that list per tile, you have one list per tile, but now you also have smaller lists for groups of 8 by 8 pixels, and then you have smaller lists for group of 4 by 4 pixels, smaller groups for 2 by 2 pixels, and then finally one very short list of entries for each individual pixel. And basically, as you keep going through the Gaussians, as you keep going from coarser to finer, you are capable of storing for each of these subsections of a tile the so far best match of a sorted sequence of the Gaussians and where they would be if you actually sorted them according to the depth value at the center of the current subtile. So this gives you something that is very, very close to actually rendering with per pixel depth values and is basically at the end of the day indistinguishable from real per pixel ray tracing or per pixel depth resolution, which is much, much slower, but with this approximate approach, you basically get the same quality at almost no additional runtime cost. So, if we can bring this now all together and look at some nice applications, we actually see that with those smaller models, we can now have also the rendering without any artifacts with stop the pop. So if we bring all of those together, we get the idea of, hey, we could use this to address all of these cases that are very, very problematic if you have modern display scenarios. So for instance, a head-mounted display for virtual reality. So think HTC Vive or think an Oculus headset. And we can, for these particular setups, if you've ever tried to look at the 3D Gaussian splatting scene inside those head-mounted displays, you probably initially had a heart attack because immediately those popping artifacts and those very nasty runtime delays from the large scenes basically give you a terrible, terrible experience, right? So if we, starting from the original 3D Gaussian splatting scene, apply our way of compressing down the scenes, we have the runtime issue solved. So now there's no more stutter. So we actually get a nice, very clean 70, 80 frames per second. And you then, on top of that, apply what we just discussed, the removal of these popping artifacts. And then maybe for good measure, you still sprinkle it with some foveated rendering so that you actually get a performance or a frame rate of more than 90 frames per second. And you end up with a comparison that looks, for instance, like this. So initially, the 3D Gaussian splatting scenes would look in VR something like this, right? So there's significant popping going on, there's significant overlaps going on, and there's a lot of this blurry artifacts of just large Gaussians being everywhere. Now, this gets worse, as I said, when you compress the scene down. You now have fewer Gaussians, and that means they are on average larger, and the popping becomes even worse. But now we have a compressed scene, and we apply stop the pop, and suddenly those artifacts are gone, and the scene is still small. Well, they're not entirely gone, right? But if you combine it with an additional approach that actually some other researchers, apart from us, discovered, which is optimal projection, this is starting to look pretty damn good. And then if we sprinkle on top of that the foveated rendering, we get a few extra frames per second that pushes us over 90 frames FPS, which is really quite nice and already is becoming quite usable for VR. So, yeah. That is a long-winded way of talking about the journey from the initial method of 3D Gaussian splatting into something that is now compact, that is portable, that is easy to render, and artifact-free, so that we can have them in immersive, portable, and low-power scenarios and on low-power devices. So, can we go even further? So the Gaussian models are now compact, they are controllable, and they are robust to render. The question is that the end of the story? And of course it's not, because you can always go bigger, right? We found a solution to take those 3D Gaussian splatting models and bring them down from millions to 100 or thousands, and that worked. But I've always been showing now, the entire time I've been showing you these small scenes, right? Like this one truck, or this one room, or maybe this one bicycle, right? I've always showed you those very, very small scenes. And of course, you can do them with maybe a couple of thousand Gaussians and it still looks nice. But what if I want to do an entire city? How good can an entire city look if I just throw 10,000 Gaussians at it, right? At some point, you hit diminishing returns. At some point, that just doesn't work anymore. So you can always go bigger, and professional datasets and official datasets will contain millions of images that cover kilometers of distance, kilometers of space. So there's a strong motivation to take 3D Gaussian splatting actually to the megascale, so that we can do entire buildings, districts, or maybe even entire cities, right? So this is what brings us to level of detail 3D Gaussian splatting, where we are trying to scale up the approach. And this is now an actual fly-through through a reconstructed 3D Gaussian splatting scene. And the fact that we can even render this is because of some very serious efforts that we made to make sure that at any point in time we have all the information available of the scene that we need in order to display it sufficiently, and that this amount of information is still enough to fit on the GPU or to fit on your graphics processing unit so that it can be rendered. Because, spoiler alert, you cannot fit the entire scene that we are showing here on any GPU, on any graphics processing unit that is available today. That is the entire campus of INRIA, so of the University of Côte d'Azur, if you've never been. It's actually quite nice. It was a bit of a, I would say, rainy day, which is odd because it's the Côte d'Azur, right? But usually it is quite nice, except for that part where the capturing didn't work, but ignore that, okay? Okay, awesome. So, how did we do this? We basically applied some good old real-time graphics methodology. So we had those Gaussian splats. We knew that there were potentially millions or billions required to model scenes at that scale. So we needed a solution to basically have a way of bringing them down and bringing them down into coarser levels of detail and use them and select them whenever they were appropriate. So first of all, having collected images from several square kilometers of distance, sometimes millions of images, first of all there needed to be some separation into spatial regions, which we call chunks. And then for each of these chunks, basically we would train 3D Gaussian splatting models. And then for these 3D Gaussian splatting models, we needed to develop an adequate level of detail representation. And this was feasible, but somewhat tricky. Not lastly because actually there was no prior literature of how do you actually combine these 3D Gaussian splats into higher or into coarser level of detail versions. And it was also aggravated by the fact that the 3D Gaussian splats were not physically representable, right? Remember that what I said, that these balls of density in space, they're not actually balls of density, they're something else, right? They are not true to the theory of volume integration. So how do you actually, of something that is not volumetrically representative, make a coarser version of that? Or how do you make different levels of detail for something like this? Well, in the end, we still had to solve the 3 standard problems of level of detail methodology that are well known in real-time rendering. That is, first of all, generation. So you have to generate those different levels of detail. And the way that we did it was basically by taking individual Gaussians, for instance 2 of them, merging them together and approximating a tight fit of what the combined density of these Gaussians, or what the combined appearance of these Gaussians would be when rendered from the outside. Basically assuming that the Gaussians are not overlapping and are almost isotropic. Okay? So this is a strong assumption, but at least with this assumption we can come up with a consistent way of deriving the function values for these merged Gaussians from 2 or more sub-Gaussians. The second problem that you need to solve for level of detail methodology is selection. So once you have the different levels of detail, right, going from the finest level where you have all the leaf Gaussians up to the coarser and coarser intermediate versions of them, you basically need something to actually decide, okay, at any point in time, which point or which Gaussian in this representation do I pick? And this is for us based on the projected size of these individual Gaussians, and then picking a cut through the tree of available intermediate and leaf Gaussians, so that we have for every path through the tree the first Gaussian that satisfies the projected size criterion onto the screen. So for instance, we pick, going through the tree, the first Gaussian from the top along each branch that is no larger than 4 pixels when being projected to the screen. And of course, in order for that to work, there has to be a hard constraint that a Gaussian, that is a child, cannot look larger than its parent when being projected, which needs to be enforced in order for this to work consistently. And the last one is switching. So basically, LOD, the third problem that you need to solve is how do you switch between a LOD that was adequate in the previous frame and now no longer is, because now you need either the coarser or the finer version. How do you go from one to the other? Because if you just hard switch them, you are back to popping artifacts, right? So here, again, we were able to derive a mathematical solution for doing a smooth variation or a smooth transition from the parent Gaussians to the individual child Gaussians, so that the popping artifacts do not come back now that we've worked so hard to avoid them. So, for completion, I have provided the formulas here for clustering multiple Gaussians into one. Those are actually derived from previous work, which was in part authored by Wenzel Jakob, if I remember correctly. So this is known stuff. So taking Gaussians and combining them is fairly straightforward. This particular method is known to actually minimize the Kerbl distance between the merged Gaussians and the pair of the original 2 Gaussians. Having the level of detail representation, we can now basically switch and train individual layers during training. So we actually are doing, after generating the level of detail, we are not directly using those generated LODs, but we are going to fine-tune the individual layers that we created, because that formula that we showed was actually already quite decent, gives you a nice initial construction of level of detail representation, but it was not yet the best that we can do. So we add a little bit of extra flavor on top, and we optimize the Gaussians. Even after having created different levels of detail, we still optimize each individual layer during training randomly. And with that, we end up with a level of detail representation where, with the generation and the selection and the switching techniques that we just applied, we can make a streaming renderer that for each point in time chooses the adequate cut of Gaussians, makes sure it's available on the GPU, streams them down, and also over time, as Gaussians become no longer necessary, evicts them from GPU memory. Now, this video here is basically George Drettakis, again, on his bike, his beloved bike, taking the trip through Nice, as he often does. Actually, he cycles every day from Nice to INRIA, which is, I think, easily more than 20 kilometers, and he does that every day, back and forth. So within Nice, he also has some favorite tours or some favorite cycles that he likes to go through, and this is one of them. Basically covering a large part, I think more of 7 kilometers of the city of Nice. If you've never been, now you get some nice impressions. In the end, basically we are approaching 3D Gaussian splatting at city scale with this. The last part of this journey is the project that we did last year in collaboration with Carnegie Mellon University. And this was our effort to taming 3D Gaussian splatting. So we actually had these initial approaches. We had the methodology, we had ways to compress it, we had ways to make it portable, but still the method was not really controllable. Also, the training speed, as we said initially, was adequate, but as we can see here, actually, things can be a lot better. And why is that? So here's the part that we haven't discussed yet about 3D Gaussian splatting, and that is when we start from the initial points that we are given, either those are random points or maybe those are points that we get from structure from motion and then we optimize them, we might not get all the details that we need, right? So if we start from a certain set of points, who's actually tells us that this initial set of points is sufficient, Usually it isn't, right? And also, I said, in the end, we end up, or we can end up with millions of Gaussians. So how do these millions of Gaussians even get there? They get there because we increase the number of Gaussians whenever it is necessary. So we do this by, during the optimization, looking at what the Gaussians are doing. And when there is a high positional gradient in the optimization, we actually assume, well, there's a lot of movement going on. Why is there a lot of movement going on? Because those Gaussians cannot seem to fit what they are trying to fit. So very likely, they just need more help, right? They just need more expressivity to actually model what they are trying to model, okay? And then basically we densify those regions by adding more Gaussians in those places where we have a high positional gradient. And there's another interpretation, or there's an additional way to interpret the positional gradient argument, and that is it can be caused by discontinuities. So between the current rendering and the target image, if there's a discontinuity, we actually want to put some Gaussians there, right? So we see here, for instance, at the top of this shape, where the light or the cyan is the current reconstructed one, and the blue one is the one we are trying to model, we actually see there's a discontinuity at this top edge. So here, we would explore, or we would obtain a high positional gradient because we have an obvious discontinuity. And exactly there is where we actually would want to put additional Gaussians, because obviously some more are needed there to grow the full shape to its completion. But also on the shape itself, so when there is a hard border, or when there is a fine detail or a transition in the images, basically that also will give us discontinuities. Now, whenever there is a hard border, or whenever there are fine details, clearly you would like more expressivity. Clearly you would like more primitives there to actually model the scene, or actually model all of these fine and potentially very sharp edges. So again, the positional gradient is a nice indicator for putting Gaussians in new places. Now there's some weaknesses, because the densification occurs primarily in areas that are already dense. So the final model size, using this very basic strategy, is actually not very effectively controllable. And there's no known method for introducing some smart priors. So taming 3D Gaussian splatting basically looks at this somewhat chaotic densification approach and says, well, let's put some method into this. Let's actually very measuredly and very concretely do this densification in the way that it becomes controllable, right? And it does this by taking multiple metrics, taking multiple measured values from the individual photographs that we have available for our training, and combining them into a function that allows us to determine an importance for each individual Gaussian and its likelihood that there should be more densification going on. And this is paired with a fixed budget. So basically now, for the first time in 3D Gaussian splatting, we can say that we want the final model after training to be a certain size. Let's say 10,000 Gaussians. Why would that be interesting? Well, for instance, because maybe you have some downstream application, like a neural network or some other machine learning structure, and that expects some inputs of a fixed size. Let's say 10,000 samples every time, right? So now the ability to actually specify upfront how large should the final reconstruction be, how large should this radiance field that you get out be in terms of parameters, becomes quite interesting. So that is why we have introduced the method, or the ability to budget the Gaussians that are coming out. And this budget basically also has a very nice attribute. It is enforced in such a way that the count of the Gaussians is only ever strictly increasing. So there's no fluctuation in the amount of memory that you're using or in the model size that you have. Basically, it always just goes up continuously from the initial number of Gaussians to the fixed budget that you have, with no nasty surprises in between, like requiring terabytes of RAM suddenly and going out of memory while you're doing the training. Also, the training is now significantly faster with some optimizations that we made through careful 3D Gaussian splatting runtime analysis. So basically, we took a look at the entire process and figured out where the time for training is effectively being spent. And we basically found out there's some significant and quite unnecessary overhead in optimization steps, in the backward propagation of gradients, and also in data movement. And again, this was done with the team of Markus Steinberger in collaboration, and that is why this GPU engineering aspect worked out so well, and we were significantly able to cut the time that is used for training by a factor of 4 to 5 times, and sometimes even more. So overall, basically comparing the original 3D Gaussian splatting training and its somewhat weird and unpredictable behavior in terms of time, size, and memory requirements, the approach that we had come up with taming 3D Gaussian splatting was smooth, fast, and controllable, so basically a significant leap forward for training. Now, finally, a little outlook towards the future. I want to talk about lightning fast 3D Gaussian models. So basically faster than a couple of minutes. Why is 3D Gaussian splatting actually still not optimal? Well, if you look, for instance, at what's going on here during the optimization of this nice bike with its detailed spokes, you see how actually chaotic the optimization is if we take a really close look, right? You see all of these Gaussians appearing, and they're going into the right direction. They're doing the right thing. They're modeling the bike and the spokes, and then they're adding, and then they're going away again, right? And then there's spokes, and they disappear, and then they move, and then they're gone. And okay, right? So very, very chaotic way of actually getting to, or even close to, that global minimum that we are trying to achieve. Now, the solution is, of course, that you only need attention, as we already know, right, from previous machine learning. And so Jordan and colleagues in 2024 came up with using per pixel information for each individual reproduction, so each individual scene. So you basically use multiple views again, and you come up with a transformer architecture plus attention to predict per pixel Gaussians. So basically for each individual image, you predict a set of Gaussians in 3D space, and then basically merge them together to get a representation. And this first approach was published as Pixel Splat in 2024. Actually a very nice approach that tries to make some very systematic assumptions about epipolar attention and how you can exchange as much information between the two images via some 3D bias, but was eventually outperformed by GSLRM, which only used exhaustive cross-attention. So basically making the model simpler, removing the bias and removing the information that this is a 3D scene and that there will be epipolar information shared between two views seeing the 3D scene. No, you get rid of all of that assumption, you get rid of all that information, and actually performance goes up, surprisingly. Yeah? This is what happened in GSLRM. And then finally, we had the mix of transformers and the lessons that we have from large language models, Mamba, this non-quadratic architecture, or this non-quadratic way of actually combining and computing the attention between all the parts of an image can actually give you still significantly good results. So by applying these lessons from large language models to the concept of attention for transformers being used to predict per pixel Gaussians, we actually have an approach that can, in a very short amount of time, so I believe this is somewhat in the order of a couple of seconds, come up with 3D Gaussian splat reconstructions from a set of up to 32 images, right? So if you use those architectures and if you use those machine learning architectures, usually you run into some sort of the necessity to do some size restriction and do some fixed sizes. So again, these models here run with a collection of up to 32 images. And this is because basically when you train those strict machine learning architectures, it's a little bit tougher to make those input sizes so variable and get still consistent good results. Now, is that the end, or is it now basically solved? I would say not quite yet, because the highest quality approaches are also the least structured. So for instance, the long LRM and the pixel splat approaches, they have a tendency to overfit very well to the views that they have, but have seemingly very weak extrapolation. So if you compare those immediately, those lightning fast predicted 3D Gaussian splats to the actual optimized 3D Gaussian splats, you usually get very poor extrapolation as soon as you move away from the initial views that you have provided, okay? And they are also, due to that, likely much less usable for tasks other than novel view synthesis. So anything that we talked about previously, human avatar reconstruction, for the dynamic 3D Gaussian splatting or dynamic scenes reconstruction, surface reconstruction, all of these are probably much, much less likely to work with those instantly predicted 3D Gaussian splats, which can be generated in a couple of seconds, granted, right? But have those properties, those very poor extrapolation properties, and those less generalizable properties. However, if this trend continues, and if there is a very, let's say, sophisticated and informed combination of injecting learned knowledge and learned expertise into these structures, maybe expanding on the initial pixel splat approach, but making it more informed, making it more contrastive, making it more coherent, and integrating some real-world knowledge into the prediction of these per pixel Gaussian splats. I think there's a huge amount of benefits that could come from that, from a truly instant, accurate, and generalizable prediction of what a scene looks like from just a couple of images in a matter of seconds. Okay, so this is basically my outlook of where 3D Gaussian splatting might be going next. And with that concluded, yeah, I end my talk. And yeah, once again, thank you all for sticking around and for paying attention and for being so brave to sit through this entire last talk for the seminar on the CHESC conference. So yeah, if there's any questions, I'll be very happy to take them. Thank you.
Thank you very much for this great, insightful, and very understandable talk. So I guess there will be a lot of questions. I would take also the second microphone, and you can raise your hands if you already have some.
Thank you very much for a very interesting and exciting talk. My question goes back to one of the papers you were mentioning, where you were comparing rasterized Gaussians with ray traced Gaussians. If you'd use efficient ray tracing, so if we had a data structure that would efficiently organize Gaussians,
yeah,
then maybe some of the performance issues would be gone, and there would be no need to do this specific sorting and the stop the pop method and so on. So do you think there is a potential that at some point ray tracing Gaussians can be at least comparable or faster than the splatting approach?
For sure. So I haven't touched, it would be impossible to touch on all the methods that are going on. So in this talk I stuck to rasterization methods because of their greater portability, right? So, but there are very concerted and very structured efforts, especially from the guys at NVIDIA, to take 3D Gaussian splatting and then ray trace them, and they're doing this very, very efficiently already, right? We are seeing methods like, for instance, I believe the correct acronym is 3DGRUT, for ray tracing of Gaussian, using the very capable ray tracing hardware that NVIDIA's GPUs have. So the latest status that I'm aware of is that these approaches are becoming more and more efficient, but as far as I'm aware, are still like 2 to 4 times behind in terms of the original 3D Gaussian splatting rendering, and now we're not even talking about the acceleration methods that we saw, right? The compressed scenes and what they are doing, and any kind of other additional culling that have been added on top of the since it originally came out. So they're definitely getting there, it's definitely viable, but I would say it's, in terms of strict ray tracing, it's not quite there yet.
Okay, thank you very much.
Okay, thank you very much for a very interesting talk. So I am collaborating with the guys doing digitization of cultural heritage, and they have this standard pipeline of doing a lot of photos and then doing photogrammetry with like capturing reality software and stuff. But they have problem with very reflective for example, golden objects or objects with golden parts. And right now they are using like just polarized filters and doing photogrammetry with these photos with polarization, but then the gold doesn't look right, as you see. So do you think Gaussian splats are the answer for these problems?
So we're talking about complex, let's say, refraction and reflection, both of them, right? So we have actually looked a little bit into reconstructing glassy objects and looking at glassy objects. And this is a weak point for all of these novel view synthesis approach, because basically what they're trying to do is to match the appearance of something. Now, if you look at something like glass, the easiest way to model glass is by doing nothing, right? If it's see-through. And only take care and actually only place density or Gaussians where you have those maybe high frequency reflections, those high intensity reflections, and nothing else. So there's a additional paper by Yorgos Kopanas where he specifically looked at highly reflective objects, and he basically had a very tailor-made approach for scenes where it is known that there are highly reflective objects in there, and basically coming up with a special solution for them and optimizing two, I believe, neural networks for representing both the standard scene and another one for the reflective objects themselves. And that worked for reflections. For refractions, I would say it's still pretty much an unsolved problem. So all the approaches that I have seen are just trying to tweak the 3D Gaussian splats or the NERF methods to actually do something with a glass structure or similar. But it's like that there's no new There's no stroke of genius right now for these challenges, as far as I can tell.
Okay, thank you very much.
Sure.
Hello. You talked extensively about the compression of Gaussians in scenes for download speeds. I have seen a paper a long time ago, and I want to ask you if this approach is still viable or considered, where they encoded these 3D Gaussians into a texture, and they tried to use an image compression algorithm.
So did you see that online, like in a blog post?
I think it was a paper.
I think it was a paper, okay. So I think that the first guy who tried to do this was Anshul Patas, who did something like this, basically, as you said, right? Sorting the Gaussians, or sorting the attributes of Gaussians, let's say, for instance, by position, right? And then storing all of these attributes into textures and then applying texture compression to the attributes. I think he was really early with this, and also he didn't publish it anywhere, he just put it out in a blog post, right? Is that the way to go? That's really, really tough to tell. The evidence has shown that these approaches lag behind more sophisticated ones. There's actually a whole site, or let's say a whole repository dedicated only to compression of 3D Gaussian splatting. I think it's called 3dgs.zip, and it will basically compare the latest methods of compression for 3D Gaussian splatting datasets and also what they achieve. So I think if you want to stay up to date on what works best so far, I would recommend to check that out, and that should give you like the most up-to-date idea of what you can do. But I think that those approaches, like storing it as images, using image compression, very nice and very creative, but I think is not among the ones that work the best so far.
Thank you.
Sure.
In the beginning, you mentioned that you need the structure for motion initialization and the camera poses, and that the MCMC method they can start from random noise.
Correct.
But what about the camera poses? Do they also do they need the initialization of the camera poses?
Yes.
And if you want to do lightning fast Gaussian splatting, do you see potential that the poses can be estimated together with the novel view synthesis, with the Gaussians?
So this is where we're entering some interesting territory, because now the question would be, what kind of assumptions can we make about the data, right? So if we say this is a potentially completely random set of images, I have no idea in which order they were taken, this would be, I'd say, somewhat challenging. So we have methods that actually do a good job for a limited number of views for predicting and giving a nice idea of where the camera poses are, right? Like Duster, for instance. If we say we have some assumptions about those cameras, for instance, they were taken in a sequence, then this becomes actually very feasible, because then we can run some simple estimation of the camera positions, which are very cheap to do, and from those then, as you said, jointly optimize the Gaussians and the camera positions together. So yes, that is very feasible, but if I were you, maybe you'd want to wait like another month before you start working on this exact topic.
Okay. Thank you. And a quick other question: the white bicycle, is this the same bicycle was taken for the hierarchical Gaussian splatting?
No, because the bicycle. So this bicycle that I showed previously is from the MIPNE 360 dataset, which was recorded by, I think, John Barron, right? If you looked at the MIPNE 360 dataset, I think half of it is just John Barron's house, John Barron's favorite park, John Barron's favorite tree, right? That's the MIPNE 360 dataset. And the bike that was taken around Nice, that was simply George Drettakis' like racing bike that he took, so no relations.
Okay, thank you.
Thank you for the nice talk. I have a question about the optimization. So are there still some challenges with maybe some local optima, or sometimes you might not even know when to finish if it's done? If you can get stuck somehow and you could have kept going on and it suddenly increases significantly. So is this still something that's researched, or what is your opinion on this?
No, absolutely. So that's absolutely a problem, and that's also a sort of what I tried to show with the densification and how random it is. And it is that random because it has to be, because if it's not that random, it tends to not escape the local minima, right? So this random behavior that we saw initially, that we saw in this video, is somewhat by design, because if we don't have it, the things that are right from the beginning converge quickly, but we don't get the things that we missed initially. So we will basically be biased towards what the SFM points give us, and basically focus on that and lose everything else if we have no sort of random behavior, like no random exploration basically of the landscape, right? So this random behavior is trying to introduce some exploration into the optimization as well. And I think the best approaches, or the best theory that goes into how this exploration can be done in a principled way, is again the Markov chain Monte Carlo theory and the corresponding paper by I forget the name, but Andrea Tagliasacci was involved in the research. So I think that's the most sound, and its follow-up works are the most sound piece of research into that direction.
Thank you.
Sure.
More questions?
Thank you, and thank you for the talk. I was wondering, for the hierarchical approach, did you consider a top-down optimization to maybe obtain some low-quality, quicker results?
Can you elaborate?
So splitting the Gaussians instead of merging them.
If we look at 3D Gaussian splatting and the way that it densifies, inherently there is already some sort of top-down behavior from the beginning, right? And we rejected that concept because initially already you could assume the Gaussians that are being densified, if they're doing this top-down densification, right? Starting from a few and then splitting and splitting and splitting. In theory, you could already turn that into a hierarchy. Like every Gaussian that is split into two could just become two children and a parent, right? But now you are restricting the behavior that we just saw, where a Gaussian splits into two Gaussians, right? And one of them just, right? So now you no longer have that opportunity. And it would be very easy to argue that if you have a Gaussian that splits into two, and one of them just darts off into the distance, and now you're turning those two basically into a parent-child relationship. Now if you want to go from the parent to the children, you basically have something that splits suddenly from very localized Gaussians to something that might be very spatially distributed. There is some work that I personally saw that tries to do it top-down, and it works surprisingly well, but as far as I know, it hasn't been published yet. So yes, it can be done, and it might have been the smarter thing to do from the start, but it hasn't been sufficiently peer-reviewed yet, and it hasn't been published yet. But yes, it seems promising.
Okay, thank you. And maybe more of a general question. How do you keep up to date with your own field, basically?
With the, sorry, with
With your own field.
So I think I checked out like half a year ago. So up until then, it was somewhat feasible, but I think like 6 months ago, I just started ignoring the subjects that I definitely have no strengths in. Like for instance, avatars. I know very little about avatars, so I can't follow it that much. And basically at some point I had to limit myself to the things that I know I am comfortable with, which are the performance aspects. So yeah, I come from a real-time rendering background, so when it's about performance, that's where I feel most comfortable. So short answer, I can't, right? So yeah, that's it.
Still focusing on your topic. Okay, thank you.
Hello, thank you for the presentation.
Sure.
I have a question in regards to optimizing the Gaussians, where you said that at the start you basically go through the scene or go through the Gaussians and remove the ones that maybe don't contribute so much. And then in the end, you introduced a method that basically you give a limit of how many Gaussians you want, and then it represents that scene with this limit of Gaussians.
Correct.
And now, my question is, how do these methods compare? So if I were to start with a scene and limit it such that I reach this limit, or then I would run the method you presented at the end and give it the limit, which one would be better? Do they converge to the same result?
Usually, if you're looking at quality, so this is a trade-off. If you look at quality, then usually the one that just keeps adding Gaussians and then prunes them again is more free to explore, right? So just by having this additional ability to explore more, by going up in terms of the number of Gaussians and putting them maybe in very weird places, it will usually lead to higher quality. On the other hand, the approach that just keeps growing and ends up with this fixed budget has no nasty surprises in terms of memory usage. So these most efficient approaches, like for instance, mini splatting, which do exactly this adding and pruning very intensely at their most demanding points during the optimization, they use 10 times the memory of what the final model actually is, right? So that's a very significant amount. That's a very significant investment of memory that you have to give the training process in order to end up with something that is 10 times smaller. So yeah, it's a trade-off, and it comes down to this problem that was also mentioned by a previous audience member, basically saying what is the optimal way to explore, right? If we know the optimal way to explore the domain and we really put the Gaussians only where we need to put them, then they should be equivalent in terms of memory, they should be equivalent in terms of quality, and the one that is just strictly increasing would be winning out, right? So if you have the perfect exploration strategy, combining it with something that is fixed budget would be ideal, yeah? But that's still a bit challenging.
Thank you.
Okay, if there is some last question. If not, let's thank Bernhard again.
Swim to the beach where the pixels play, from rendering to VR. It's a pixel away.